Hi, everyone. I'm very happy to introduce Wei Wen from Duke University to give us his research presentation on efficient and scalable deep learning. And so many of us are working on deep learning or in the area of related to deep learning, right? Especially in nowadays, we love to train large models such as BERT and GPT. But here, Wei is going to share a very unique perspective of deep learning, where he focused on the efficiency of deep learning. In particular, he focused on model compression and distributed training and AutoML. We also have rich industry experience. He interned with MSR here and interned with Google Brain and Facebook AI. And now let's learn from Wei.
Thank you, Chen. Hi, everyone. I'm Wei from Duke. Thanks for coming. I'm really glad to be here since I did like 2 internships here, and I'm trying to get myself upgraded. So topic today is about efficient and scalable deep learning and beyond. So the general trend of deep learning is we can always get better performance if we are able to train larger models, given we have a lot of data. So here is a figure which covers the majority of the computer vision models. And the x-axis is the computation cost. Y-axis is the accuracy. So in general, if we can build a larger model, we can always get a better performance. This is typically true for one specific neural architectures. For example, for ResNet, we can get better performance if we can get deeper neural networks. And this is similar for like inception model. And similarly, in natural language processing, we also get a similar trend. So if we can, here is an example for language modeling and on Wikitext. So if we can build a larger model, we can get a better perplexity. So we are still curious about how can we go below if we can still build larger models in NLP problems. So the question is, why don't we always build a larger model? But there are obstacles. The first obstacle is on the training side. Since training a larger model is very slow, so if we have a new model, we want to evaluate. So we want to check is this new model is it good or not. Then we will take a longer training time to get the feedback. So usually we have to evaluate a lot of models before we find a good model. So this one will, if the model is too large, it will extend our research cycle and production cycle. The second obstacle is on the inference part. So after we build a model, eventually we want to use it. But if the model is too large, the inference time is very slow. So it will be very challenging to deploy those models to applications which have very limited computing resources or memory resources, like in Microsoft HoloLens. So my research in general is trying to make the training faster and also inference faster, so we can build a larger model and also to make those models deliverable to like applications in real industry productions. So here is outline. I'll first introduce my previous research to make the training faster, typically in distributed training systems, and also my research on sparse neural networks to make the inference faster. And finally, I will introduce my future research. So let's go to the first part. How can we make the distributed training system faster? So I'll focus on one work I did on Ternary gradients to reduce the communication in distributed deep learning. So here is a little bit background about distributed deep learning. So in synchronized SGD, we have a sender parameter server, and we first split. We send the parameter to multiple machines and train those models in parallel, but using different data. After the training is done, at each machine, we will synchronize the gradients to the sender parameter server, and this finishes one run, one iteration, though it will keep doing this again and again. This is good because we have a lot of machine, which means we can train faster. But we have a problem. We have the communication bottleneck problem. So in general, if we have more machine, then we can always reduce our computation time. But since we have more machine, which means we have more synchronization over the network, so the communication time will increase. So your total time will saturate at some point. So you cannot go beyond one point. So it limits the scalability of distributed deep learning system. So my research goal is trying to reduce the communication time and make the distributed training more scalable. So that's simple. So in distributed training system, we can slightly change the communication pattern that we only communicate gradients over the network. So each worker will compute the gradients and send over the sender parameter, which will average the gradients and send back. So we only communicate gradients over the network. So usually gradients are floating precision, which have 32 bits per element. So
can you explain the location?
Location?
Location. What is J in red and what is J in blue?
So rotation here, W is the weights, and G is the gradient. And so at each worker, it will first compute gradient on each data. So it will send to the parameter server, and it will average all the gradients from all the worker and get the averaged gradients and send back. Then each worker will be updated by the averaged gradients.
So you assume the model has n copies.
Yes.
Then all the models are always the same.
Yes.
So they are updated by the same gradient.
Yes. So the initialization is the same. So the updates is also the same. So it will always be the same as long as we use the same.
So you only distribute the train data on each node.
Yes.
The model is
in the worker. Yeah, and they use the same initialization seed, so they will be always the same. This way, we can only communicate the gradients, and I will explain why it's beneficial to only communicate the gradients over the network. So usually it's 32. In this work, we do quantization. We reduce the precision to only three levels. So only three discrete values. We call this ternary gradients, TernGrad in short. If we can successfully do this, we can reduce at least 16 times of reduction of the communication. So this will be very challenging because it will lose a lot of precision in the training process.
I think previous Microsoft researcher did they use like cheap updates of gradient.
Yes, I'm aware of that. Yes.
Yeah.
Yes. So the basic idea is simple. So before I go to the detail, let's go one step back. So when we do distributed training, or in the supervised learning in general, we want to minimize the averaged loss over all the training samples. And the gradients can be updated by the gradients from all the data set. And N is usually very large, so the computation is very costly. So in deep learning, usually we use a stochastic version. We randomly sample from the data set, and we use the sample gradients to estimate the original batch gradient. It works well because one reason is the expectation of the gradients is the original batch gradient. So it's unbiased. So if so, why don't we do quantization in a way such that after the quantization, we still keep the expectation? So here, the motivation is we do ternarization on the floating gradient, and we want to keep the expectation is as the original gradient. So it's a still unbiased gradient. So that's the motivation. So how can we do it? It's simple, actually. So this one is the floating gradient, and we first get the sum of all the gradients. And then we have a scalar, which is small, usually very small.
Do you predefine ST or is it verb?
It's either not learned. So ST is the maximum absolute value of all the gradients. So, okay, so we have those two parts. And then I do element-wise multiplication with the binary code, which is either 1 or 0. But this one is a random variable. So it's basically Bernoulli distribution. The probability for each element, its probability of being 1 is just the absolute value of the gradients over the maximal scalar here.
What is K?
K is the index of the gradients. So yeah, we have K gradients.
Coordinate.
Coordinate. So the index of GT is all the gradients, and they have element-wise multiplied by a vector. So K is the index of the vector, which is a binary code like here. So let's go to the example. So let's say our floating gradient is like this value, and we get the maximal absolute value, which is 1.2, and then we get the sum of all the gradients. Then we form a Bernoulli distribution, and its probability of being 1. So let's say for this element, its probability of being 1 is just 0.3 over 1.2. So it's simple. And then we draw a Bernoulli distribution from this probability. We get the sample of the binary code, and we multiply all of them. So if we do in this way, we do a little bit of math here. So the expectation of the quantized gradients is just the expectation of the original one. So it's unbiased. So we keep the expectation, but we do increase a little bit of variance. But I'll go more detail about how we reduce the variance. So then we only need like 2 bits for each element and one single floating value. So it will significantly reduce the communication volume.
Can you explain the intuition here? So for example, why do we need BT?
Why do we need BT is we want to draw a Bernoulli distribution. Because so first the value, eventually the value is just 1 or 0. So it's binary. So the precision, we can so there are only 3 possible values here. Then we can encode it in a very low precision.
So 3 values is 0, 1, and -1.
And 0, minus A, minus ST, and ST. So there is a scalar, small scalar here.
Excuse me, how did you get from the last line? How do you get from the bottom, the final line? How do you get from this to that?
This
Yes.
here? So here we have expectation over 2.
Yeah.
And then we get expectation over Z and the expectation over B given Z.
Okay. Yeah, that's it.
So
yeah.
this one have low value related to Z, so it's gone.
Yes.
Then this one is just B, so we get there.
Okay, so but how is the expected value of B equal to the expected value of G? That I don't follow. I think I'm missing something.
This one?
Yeah, so how do you, yeah, exactly. I just want to see your simplification here. How do you simplify this?
Because the probability, the definition of probability,
Yes.
the probability is just GTK over ST.
Yes.
The fixed expectation, you just get
Yes.
GTK, original GTK back.
Yes. Yeah, it's a basically like variable stuff. So we can talk detail, but it's just the production. So let's say what's Z? Z is just the data. So we only care about BT. So the BT is the expectation of BT is just the probability. The probability, which is this one, and then you multiply this one with this one. It will reduce to that one. Okay, we proved the convergence of TernGrad. And this one is the basic assumption to prove the convergence of standard SGD. So it's standard, it's not ours. So to prove the convergence of TernGrad, we do need a little bit stronger assumption on the gradient bound here. So in the standard SGD, the L2 should be bounded, but now we require the multiplication between the maximum norm and L1 norm bounded. So this value is always larger than this value, so TernGrad do need a little bit stronger bound. But we propose some tricks to make those two bounds closer to each other. So one is layer-wise ternarization. We do it layer-wisely because different layers have different distribution. And we also do gradient clipping to limit the range of the gradients. But details is in the paper. So evaluation, we evaluate on ImageNet, on LSTM. So on LSTM, there is low accuracy loss, even using 3 discrete values in the gradients. So in some cases, we even observe higher accuracy. Because when the large batch size is very large, the variance is too small to learn well. But the variance from the quantization will help the exploration. And here is the convergence curve comparing with standard SGD. So the convergence also the same. And we evaluate on GoogleNet, we observe some small loss, but on average it's 2%. One thing I want to emphasize is we didn't do any hyperparameter. All the hyperparameters are used from the standard SGD, so we just use it. We use the same learning rate, we use the same batch size, we use the same total epochs. But we could get a better accuracy if we tune them.
So, have you ever tried that? In the beginning, you use your TernGrad to train, but in the end, for example, standard training will decrease the learning rate. For example, after you decrease the learning rate twice, then for the smallest learning rate, you return to the full precision of the gradient. So will it kind of recover the original accuracy, or it still get a bad accuracy?
We didn't try exactly that way, but we tried like every 10 epochs. The first 9 epochs we use TernGrad, and the last 1 epoch we use full precision. Mm-hmm. It's similar. It's the same. It didn't
so
have.
You mean its accuracy is similar with TernGrad? It's not similar with the
right.
original SGD.
But I didn't try the one you said. Probably that would help.
Okay.
Yeah. So that's all about convergence, and we can reduce the communication. So in practice, how can it make it faster? So here, the speed over the number of GPUs in the distributed system, and the solid bars are the standard floating point of SGD, and the shaded bars are ours. So we can always get speed up. So in general, TernGrad can give us higher speed up if the communication time occupies a higher ratio. That's obvious because we reduce the communication. So in general, it gives us a higher speed up if we use more machine. So if we use more machine, we have more communication ratio. Or if our communication bandwidth is very low, like we can get a higher benefits if we use low-end, unlike network like Ethernet versus infinity band. Or if we train like deep neural network which have a more hyperparameter versus the computation. So personally, I think it will give us more benefits in an NLP problem than CNN, because NLP problem have more parameter over computation. Also, it can give us more benefits if we use GPU-based distributed system, because GPU compute fast and the communication is more of the bottleneck. TernGrad is in production. It's adopted by Facebook AI Infra and use it to reduce the communication bottleneck in the AI Infra. And it's evaluated by the ads ranking model, so which have a zero tolerance or the accuracy loss. They cannot tolerate any accuracy loss. Otherwise, that means a lot of money. So, and it's also available in the PyTorch. So this finished my first part to make the training faster. And I could take one question if you have.
I see you tested all the use STD, right? Can you test all the adaptive learning methods, for example, Adam?
Yes. Yes, we tested for both momentum and Adam.
What's the result?
It's similar.
Similar, okay.
Yes. Okay.
So, can you give an intuition why you can, why you can reduce the quantize the gradient so much and the final accuracy is still roughly the same?
Because the variance, you have higher variance. You keep the expectation, but you increase the variance. So, yeah.
Okay.
So I'm going to move my second part of research on make the inference faster. So inference acceleration. I did a little bit more research on this LAM. So I'll even try to put a new network with a chip which only support a spiking neural network. And I also tried to cluster the neurons of the sparse neural network and make the wire congestion in the circuit design be more efficient. But I wouldn't go too much detail. I will only focus on two research here on sparse deep neural networks. By the way, one of the work was published when I was an intern here. My mentor was Yu Xiong. So when people talk about the sparse neural network, usually they refer to a neural network which have a lot of connections are removed. It can significantly reduce the storage size of a deep neural network. And if we can customize the hardware for the specific neural network, they can get a good speed up. However, when I measure the speed on a general platform like CPU or GPU, the story is totally different. So here is a sparsity. We get like 95% of sparsity. But when we measure the speed on the CPU, on the GPU, the speed is very limited. In many cases, when the speed up is 1, which means the speed is the same. So the speed is very limited. In some cases, it's even worse. So why? Because the sparsity is non-structured. It's randomly distributed, but the hardware is very customized for regular computation. But the non-structured pattern just break the regularity for hardware parallelization. And so it have a very poor data locality, so it get very trivial speed up. It's a little bit better on CPU platform. So this one is the speed up of random sparse neural network over sparsity. But it's not it's not as good as the theoretic speedup. So for example, here, the sparsity is 19%, but only 2 times speedup because of the similar issue I just mentioned in the previous slides. So to make it more efficient, so we think we should use structured sparsity instead of random non-structured sparsity. So here is an example to show the scalability of structured sparsity versus non-structured one. So when I say structured sparsity, I mean a lot of rows and the columns are all 0. So we can just remove those 0 rows and the columns and compress it to just a small dense weight matrix. So because it's dense and it's small, so it can compute much faster. So what's structurally sparse deep neural network? So it means connections or weights are removed group by group, not just one by one. So in a neural architecture, it means we remove one dense structures, like one neuron, or it can be one layer, it can be one filter in the convolution layer, or it can be one hidden states in the recurrent neural networks. And in terms of the perspective of weight matrix, it means structured sparsity deep neural network means we remove weights block by block. So it can be, so one group can be one rectangle block, can be one row, can be one column, or even can be the whole matrix. So it's predefined. So how can we achieve it? How can we learn a structured sparsity? It's simple again. So group lasso regularization is all you need. So group lasso regularization was proposed, and it's very effective to learn structured sparsity. So basically, how does it work? We first split the weights to a lot of groups. Like here is an example. We split them to 2 groups, and then we add group lasso regularization on each group, which is basically the vector length of the group. So here is the group lasso on those 2 groups. Then we add all those group lasso regularization as one single regularization, and we add regularization to our data loss function, like across entropy. So we just learn it end to end using stochastic gradient descent.
What's your criteria to split the weight into several groups?
Good question. We split. So it depends on what kind of structure you want to learn. So let's.
This is structure dependent. For example, C is different LSTM.
Yes. So it depends on what kind of structure you want to learn. Let's say you want to remove filters in the convolutional neural network. Then one group is all the weights in one filter. Mm-hmm. So if we want to remove one row in the weight matrix, then one group is one row of all the weights. So it depends on what kind of structure you want to learn. So we refer to our method as SSL. I'll use this one a lot. So there are more rigorous proof about why group lasso regularization can learn structured sparsity, but let's explain it iteratively. So here is the group of all the weights. So it's the vector. It's a vector. And when we do gradient descent, it will be updated by regular gradients, which come from the data loss, plus one additional gradient. This one is the additional gradient. And basically, it's just the unit vector going against the direction of the vector. So during the training, it will iteratively squeeze the size of the vector, and eventually, if it can, it will go to the 0. So it will remove all the weights. So many groups can be be pushed to zeros, then we can learn a structured sparsity pattern.
Sorry, just to clarify. You say many groups will push to zero. Is that the whole group push to zero or?
The whole group.
The whole group.
And many whole groups, yes. So here is a comparison on AlexNet. Don't laugh at me, AlexNet. It was a state of art. So, but it's fair for comparison between non-structured sparsity and a structured one. So it's fair. When I say structured sparsity, it means this random sparsity. And so here, structured sparsity, I mean I remove rows and columns. There are a lot of information here, but let's break it down. So bars here are speed up on CPU and GPU. And the lines here are like sparsity across 5 layers. And the orange color corresponds to non-structured sparsity. And the green one corresponds to our approach. So you can see the bar of the green one are taller than the orange one, which means we can give a better speed up.
Can you explain why the speed up layers are different?
Because you get different sparsity.
Is this related to some property of neural nets?
Yes. So in general, shallower network have less compact because usually you have fewer filters, but you have more like filters in the deeper layer, and also the features in the deeper layer are more sparse, so that you can achieve a higher sparsity in the deeper layers.
Do you think these properties can help you to redesign the algorithm?
Yes, then I would suggest that we don't need that much filter in the deeper layers in this case.
Actually, can you explain what's X is? Number of the layers or?
This number?
Yeah.
Or the index of the convolution.
Okay.
Convolution 1, 2.
So what's the meaning of the column and column none and the row none? So you
This one?
No. In the figure you have 4 nuns. One is weight. One is.
Okay, this is the sparsity of the. This one is the sparsity of how many weights are removed.
Okay.
This one is how many rows are removed. This one is how many columns. Or this one is how many rows. This is one how many columns.
Okay.
Yeah.
Do you lose any accuracy by doing that?
This one is 2%, but the accuracy are the same for both. They both have 2%.
2% loss.
Yeah, both. Yeah.
So for the baseline one, did you use the original paper that retrained like you prone and then retrain?
Not really. We used we used L1, but the sparsity is higher than the original paper. So this is on AlexNet, and so as I said, what kind of structure we want to learn depends on how we split the groups. So here, if we want to remove layers, then one group of weights are all the weights in one layer. So if we remove one group, then all the weights, so one layer can be removed.
Does this mean that you can reduce one layer of the neural network?
Yes, that means we can reduce the depth.
Okay, does it mean the features at the bottom layer can drop as an input for
Yes.
Okay.
Then the information can go through the shortcuts. So here is an experiment on CFA10. So on ResNet 32, we can reduce the number of layers by 14, but we get the similar accuracy. There are a lot of redundancy in the deep neural networks. And again, we can generalize it to LSTM. So again, what kind of structure we want to learn depends on how we split the weights. So we can remove, like in this case, we can remove the hidden size. So all the white strips here are the structures that are associated with one hidden state. So if we want to remove one hidden state, we have to remove all the structure in the white strips, like here. here is a sophisticated formula, but let me cover it. So if you want to remove one hidden state, that means we have to remove 2 rows and 4 columns in the weight matrix in the LSTM. So we basically group all the weights in one group, and we remove many groups. Then we can reduce the hidden size.
I have the same question, Sheldon. It seems for different models you have a different definition of the groups.
Yes.
Right. So is there any heuristics for to define these groups?
So it depends on what structure you want to remove. So in this case, we have to predefine. We predefine, say, we want to remove hidden states. Then we find all the weights associated with one hidden state.
But in most cases, we don't know which structure will be important, which structure not important. Right?
In that case, then I would just split the weights to many small blocks, let's say 8 by 8, and let it learn. Then it will learn what kind of structure can be important.
Well, have you ever tried sort of different heuristics? Say, okay, I group the parameters this way and that way, and do the comparison. Well, for ResNet, because your original goal is to reduce the layers, number of layers. So you assume each layer is a group. By this time, you say, okay, I want to remove the hidden structure.
So I would say we can put all the structure, all the regularization for all kind of structure we want to learn into one single loss. Then we can let it learn, but that would have more parameters.
So in this case, if you, for example, in the beginning, you do not know the sparse structure, so you specify maybe the hidden size, hidden dimension to be 1,000, and you put this nozzle, a good nozzle to learn the sparse structure, and then you find that, okay, I can remove 200, so finally it's 800 hidden neurons. So will you retrain the model with this 800 neurons again, or you will just use the previous one?
In CNN, fine-tuning will help, but in RNN, we find it won't help a lot. It's quite similar, so we didn't do that.
Okay. And also for CNN, just now I missed one part. So what do you mean by remove row and remove column? Because CNN it's more like weight times height times channel. So I'm not really understand what's the meaning of row, what's the meaning of column.
So that depends on the implementation of the lower level. So in general, in Cafe, one row basically is one 3D filter. But in that case, we are trying to squeeze the size of the matrix. We do it in the perspective of computation. So one row is a filter.
Okay, one row is can I understand one row is a channel?
One row is a filter. Yeah. And the one column is more sophisticated.
Okay.
But that's from the
When you remove a row, it's like removing one channel out of this hidden state, right?
So you're going back to LSTM?
Yeah, I'm talking about LSTM.
Okay.
In this case, like the white row and the
So
yeah.
all of them will be removed.
Yes, I know. So when you remove that row, in that case, it will look like this, a column and a row in each of these matrices. It's like, instead of, let's say, you had 1,000 dimension for the hidden H, now you make it 999, right?
Yes.
That's the case?
Yes.
So if you train for a LSTM for a size of 999, will it give the same result?
I'll get there.
Or there is something specific about that?
I'll get there. Yes.
Okay.
So short answer is this one is better, but I'll get there.
No, I see. I think I understand the idea. So what you're gonna get there is gonna say that no, you can't target for a small dimension right at the bat. instead you do this, so the model has the ability to actually find the right structure or the smallest, the maximum sparsity. You're trying to, okay, so is this a correct understanding if I say that you're actually searching for the right dimensions of the model? You have a method to find the right sizes for the model.
That's one benefit.
Okay.
Yeah, and then we have
Even if sparsity wasn't the case, it's just like I just want to go and find the right
Yes.
dimension. This is
Yes.
the right way to do it.
that's yes, and the speed is faster.
I don't, because in this case, this kind of the sparsity is very simple. You just see that, okay, I just first use very large hidden size 1000, and then I find, okay, 980 is a good number. So I think your question is, I think it's very related to fine tuning, or just first pick the oracle sparsity number 980 and then kind of train from the beginning.
Yes, I'll get there.
Yeah,
So
that was my question.
let's go to here and answer your question. So we use this baseline, and we have originally 1,500 hidden size. And using our approach, we keep the original perplexity, but we reduce the size. So we get a significant speed up. So to equal your question, can we train a smaller model? Can we get the same performance? So we did the experiments here. So we trained the same LSTM, which have the same hidden size, but from scratch. Instead, train the smaller from scratch, but the perplexity is much worse than learn to prove them down.
So, okay, so the reason I'm bringing this up is that there is another method that you can reduce the size, has nothing to do with sparsity, it has nothing to do with reducing rows or columns, but they do single value decomposition after they train a big matrix. So the idea is that if you were training the small models at the beginning, you will never find the same result as if you have trained a full big model and then do single value decomposition.
Exactly.
And then do some fine tuning after
Yes,
that.
yes.
So it's along
Similar
the same
here.
line.
Yes, it's similar here. Yes. So basically, a larger model gives you more exploration. You find
Exactly.
a better one.
Yeah, that's exactly what I wanted to get.
Yes, agree. Okay, so basically here is just the structure we learned. It's very regular. It means it removes a lot of rows and columns. And finally, we just inference, use the small model. So
After you find the structured sparsity, can you pack it to a regular matrix?
Yes.
To pack it back?
because it's regular, yes. That's the benefits of structured sparsity. So we basically just create a smaller LSTM, and we use the non-zero weights to initialize it. Then we get the performance. So in general, LSTM can reduce the size while maintaining the same perplexity, or we can also make the trade-off. We can reduce the sparsity regularization, get a little bit larger model, but we can reduce the perplexity, and it's better than training a smaller model from scratch.
Can you explain why you do it reduce the parameters still get that task complexity?
You mean why do we?
No, I think the second the gray line, right? You get better complexity, but still better reduce the parameters.
Yes.
I'm not quite sure if you reduce parameters, you can get better test perplexity.
Yeah, this is test perplexity.
Why is it better?
This is the benefits of SSL.
Okay.
Yeah. So basically, we can get a smaller model which have better performance. So here's a more evaluation study.
Exactly? By tuning the hyperparameter, or?
I think one single hyperparameter we changed is the dropout ratio, because we had additional regularization from the sparse regularization. Then we don't need that much regularization from this dropout. That's the only one.
So you change the hyperparameter, you can get better perplexity. Is it how that works? I mean, the green line, how did you achieve that green line exactly?
This one,
Yeah.
we use SSL,
Yeah.
and we changed the lambda regularization from
You change the
the
lambda. Okay.
yeah.
Is this PTB data set?
Yes.
this is random data set,
Yes.
because it all depends on how you do the regularization. And you only report test perplexity here if you can report the training perplexity. I'm not sure about the conclusion. Okay, for example, did you test the training perplexity?
Yeah.
Are they similar?
Yes.
Even for the last one, where you train a smaller model?
For this one?
The last one.
This one?
Yeah.
I can't exactly remember the number, so. But we care more about test. So
what's the exact meaning of those pictures in the last slide?
that means the structure, the pattern we learned. So white region are zeros, and the blue dots are non-zeros.
So what's the meaning of LSTM1, LSTM2? You learned two models?
Those are 2 layers.
Okay.
Layer 1, layer 2. Yeah. So here, basically, SSL can get a better trade-off in terms of performance and the model size. And we also did experiments on recurrent highway network, and we start from this baseline, and then we use SSL to reduce the size, and we either reduce the perplexity, or and use a smaller model, or we can keep the perplexity but get a much smaller model. So from this trend, we can see if we start from a large model, then pull it down, then we can get the benefits. We can make a better trade-off. So the implication is we should start from a redundant model and sparsify it down. So this is how does SSL work for very large model, but we are also curious about how does it work for very small compact model. So we did experiments on BADAF model, which is a smaller model, have only 2.7 million parameters, and the hidden size is only 100. In that case, because the model is very compact, it's originally very compact, so we cannot say keep the performance but reduce the size. But we can still make a good trade-off by SSL. So for example, we can reduce the size less than 1 million by only drop 2% of the F1 score.
Which is this task?
It's a question answering on squad.
Okay.
So this concludes my previous research. So summary. So we did research to make the distributed training more scalable using stochastic quantization over the gradients, and it's effective. It's effective evaluated by Facebook's AI production. So we can reduce the research cycle and production cycle because we can make the model train faster. And on sparse neural network, we can enable more ubiquitous AI on edge devices like a cell phone or self-driving car or any VR devices because the computation is very limited. And we also observe performance gain if we can start from a very large model, then prune down, specify it down.
So before you continue to the future directions, on the first one you said that you believe the TernGrad worked because you preserved the variance. Actually, you had more variance, okay?
More variance.
More variance. No bias, but more variance, and that more variance helped you in some situations. Mm-hmm. What is your understanding of why sparse? I mean, how would you explain why this method works better than, like, for example, any other method out there for exploring the size, the correct sizes of the model? Why does it work?
Why does it work? First is the deep model usually is redundant, so we can prune them down. And the second reason is comparing with long structured one, structured pattern is efficient.
I want you to specifically tell me if you have an understanding why going and searching in a bigger space and then pruning it down is better than just going directly point pointing. What I'm trying to say is that maybe we don't have a sophisticated tool to just find the right model, or you have an understanding that searching a bigger space is much better, and then bringing down gives us no loss.
Exactly.
I just want to see your understanding.
So my understanding is if you start from a large model, you have more on directions to explore, and then the pruning process will find which direction is the right direction. So you have a larger space, which means you have more exploration in the parameter model space. Then sparsification is a process of trying to find the good one.
Does the same concept of high variance gradients apply here too? Like the fact that you don't have some of these rows or columns doesn't mean the gradients are zero and therefore you have higher variance in the gradients, the gradient matrix?
From the perspective of exploration, they are similar. So
yeah, that's what I'm trying to get. I mean, can I get the same message from the first one and the second one too?
Yes, the first one is exploration in one model space.
In the precision of the gradients, and the second
one is explore in the space of the model space. Yes. So go to the future. How can we go beyond my research and what I want to do in the future? So how is my research related to recent research? So one related research is on lottery ticket hypothesis, which is the ICLEAR-based paper this year. So a lottery ticket hypothesis says for a dense, randomly initialized feed-forward neural network, there is a sub-network, which is a sparse neural network. They also referred as mini tickets. So if you train this sub-network from scratch, you can reach the similar accuracy within similar number of iterations. They only hypothesize the existence, but we don't know how to find it. So if you just randomly pick up a random sparse neural network, the accuracy will be very, very bad. So in our recent research, we found that SSL possibly can identify the subnetwork at the early stage of the training process. So in our experiments, we found that during SSL learning process, a lot of structures have a very high. The SSL have a very high sparsity in the very early stage of the training process, and those zero structure will never come back. So if so, that means we can just remove those useless structure, and we gradually remove those structures one by one, and finally we just converge to a smaller neural network, which probably is the mini tickets. So this one gives us about 40% of the training time reduction for ResNet on ImageNet. And this paper is nominated by Best Paper Students paper in supercomputing this year. And
from my memory, there's a big difference from your SLL and this lottery ticket hypothesis. Because in that hypothesis, what they find is if they find that sparse structure and then they train that, then they treat that sparsity as an oracle and then train a sparse network, then the accuracy will be recovered. But in your case, in fact, you are arguing if you given that sparsity oracle, and just train it from the beginning, you cannot reach the same level of accuracy because you lose the kind of exploration and power of first explore on a very large dense space and then finally gradually go to the sparse pattern.
No. So
actually, sorry.
Go ahead.
The lottery ticket story is that you can recover good accuracy in the smaller network if you start with the same initialization as you did before you prune. And this is a way of preserving the residue of the initialization after pruning as well.
So does that mean that in your experiment, in your summarization slides, in the last bullet point, you said that it's better to start from a dense large network and then use SSL to find the sparse network. That one give you high accuracy. So you try that if you are directly given the sparse structure and then train from the beginning, you cannot reach the same accuracy. But have you ever tried, just like the lottery ticket hypothesis, just remember your initial random initialization and then use the same random initialization and to train the sparse model? So exactly, we can redo the lottery ticket hypothesis.
Yes. So that means we can use SSL to identify the winning tickets. So that's the relationship here. So in the paper, they just did an exploration on non-structured sparsity pattern. This one is like, so we are thinking probably SSL can identify the winning tickets.
Okay, and it's also identify a structured winning ticket.
Yes, exactly.
But have you ever really kind of remember the random initialization and then train with the sparsity pattern again?
Not yet. It's an open question, yeah. But I think we worth to try. That's future work.
But even if that works, that's useless, right? Because by no way you can get the random network. So I think even that experiment shows you is get the same result. So what? I mean,
I want to understand what's the connection between SSL and the lottery ticket hypothesis. Whether they are the same thing or they are different.
Yes. That's very interesting future research. So the second related work to my previous research is AutoML. So an automated machine learning to use a machine to design machine learning model. So when the community make a lot of progress on AutoML, they find that it's much more efficient to do in this way. So they design a very large model which have all the operation options enabled in this single one-shot model. They call it one-shot model because they have all the options enabled. And the goal is to pick up an optimal path. And so the experiments show this method is very efficient for AutoML. But so the question is, can we use SSL for AutoML? So in SSL, basically trying to remove structures. So a second open question is, can we use SSL for AutoML? So another research direction inspired by my previous research is on scaling NLP problem. So going back to my statement at the very beginning, the current trend of deep learning is if we can train a large model, we can always get a better performance. This is even more true in NLP on supervised learning. So here is an ablation study for the BERT. And if they can train a large model, they get a better performance. But personally, I think NLP is in the ImageNet era, and it's very hard to further scale up because of the computation and the memory cost. So we need a more scalable training method and the more scalable base models to scale up. So one direction we can go is we design more scalable training method. So basically it means given an architecture, let's say BERT, can we make it training faster? So we could use TernGrad SSL, but what's more?
SSL doesn't make training faster. Right? SSL doesn't make training faster.
Say it again.
SSL does not make training faster.
It can. So
that you just mentioned one example. Say that.
Here? Yeah.
But you still have to have the entire architecture to reduce it. Otherwise, unless you reduce it in the training.
We just save the checkpoint and create a new smaller one.
Oh, so okay. So you reduce the size. But if you want to truly go in the original model and you want to find it, you still have to keep the original size or oracle.
But our experiments show zero architecture never come back. Rarely come back. So we just remove that and train a smaller one gradually.
Okay. Got it.
Yeah. So the second direction is design more scalable new models. So we should design a fast, accurate, and compact base model and scale up. So, and I also believe that AutoML will play a very important role in designing compact, small NLP models. So this brings me to this another future research I would want to do on AutoML. So this figure also equals to my previous statement. This is the computer vision models. And in recent years, people generally design more scalable model. So the smaller model but higher accuracy, designs more scalable model and scale up. So this model is designed by AutoML. It's not by human. So I believe AutoML will be very important in design compact NLP models in the future. But there are two problems in AutoML. The first problem is AutoML eats CPU, eats GPU, eats memory, eats everything. So it's very inefficient. The second problem is AutoML relies on human-designed operations and only search the combinations. It cannot invent any new architectures. That's the problem of AutoML. So in my past half years, I did some research on the first problem, and to make the sample more efficiency. So the x-axis is the number of a network we have to train to reach some test accuracy. So this one is a random method. This one is the state-of-art regularized evolution. And my recent research is getting here. So now we can train, we can find the best Oracle model within hundreds of samples, which we have to only train hundreds of network to find the optimal one. And we'll make it public in next month. And with that, conclude my talk and open to questions.
So I have a question with TernGrad. So apparently you transmit 2 bits for every gradient, but you only actually use 3 values.
Yes, we waste 1.
That's right. So have you thought about, is there a better, more efficient way to use 4 bits fully to make it more accurate or anything like that?
Yes. So if we use 2 bits in real production, we definitely should use 4 levels. We don't want to waste it. But that's the research we have more interested in, how can we very aggressively to reduce the precision. So in that paper, we used the 3 levels. But in production, the one I mentioned, they used 8 bits. So that's the trade-off.
Any questions? Okay, I will ask one. So let's say I want to apply SL to transformers, and I want to listen to your suggestions. Okay, I understand that SL has the flexibility that where you can design the growth, right? Just as you did for Cadence and LSTM. And let's say I want to design some growth for transformers, and my goal can be one, I want to get some interpretation.
Interpretability?
Yes, and the second one is I want to reduce the computation or speed up. I know that this could be different goals. And can you say something that how I can design the growth so that I can achieve these goals?
Simultaneously or?
No, not simultaneously. Simultaneously will be hard.
So for the to reduce the size of a model, so let's say we can use it to reduce the hidden size of the bird, or we can reduce the number of heads. So that's basically how we split the groups. For the first, on the interpretability, so usually we say simpler model is more interpretable. So if we use SSL, we reduce the size of the model, then that will be more interpretable.
Why does this? Okay, Okay, for transformers, one interesting thing is the attention mechanism, right? Okay, if I can apply sparsity to transformers, let's say if I can get something like for the given token, this token attend only a few other tokens in a sentence. This could be something interesting for people to interpret.
Then I think we can use a mask parameter to mask the attention, and then regularize the regularize sparsity. And it will, if the corresponding weights in the max is 0, that means that attention is useless.
Are you suggesting we can learn the mask?
Yes.
Okay. But I think in the current transformers, the mask now is pretty defined.
Oh, I mean, not that mask. I mean the mask over the whole attention. That's the parameter.
Oh, okay.
That's a parameter we can learn.
Okay. Thank you.
Regarding this, I think also the previous work is only focus on one task. For the protocol, this kind of models, basically it's trained using a supervised fashion and fine-tune a downstream task. If you fine-tune a downstream task, this model compression and remove some component should be easier, because if you remove for some tasks, that's some layer is not important. But if you want to compress your bird model into the general model, small model still have be very generalized in many tasks. How you can guarantee this kind of thing?
So for the unsupervised learning, people usually use language modeling.
Yeah.
So I've shown the effectiveness of SSL on language modeling, and that's one thing. Another thing is we can separate the specification for unsupervised learning and for a specific task. So given a specific task, we can specify the new parameter for a specific task.
Yeah, go back to the previous language model. Basically, you still test on same task, right? Instead, you after you compress language model and fine-tune, use this language model to fine-tune all other tasks. You haven't done that.
Future work.
Okay. So, quick question. I'm not super familiar with the AutoML sort of literature, right? But for example, the biggest thing we've seen in terms of shrinking stuff like BERT is Albert, where the way it's done is that you end up with parameter sharing. How would I catch? So first of all, there's a couple questions. One is like we probably don't have the right architectures in the first place, but related to that is that we may not have the right sort of set of actions to put into your framework. So for example, can I put into an AutoML framework, oh yeah, you should be searching over all possible sets of parameters that should be shared and not actually duplicated for the money, right? What are the kind of limits here, because we just sort of don't actually even know what the building blocks are that we should be searching over.
Yes. That's the second problem I mentioned in AutoML. It cannot invent any new architecture. So I think we could be, but the search space will be very large. So it will take very long time. So for example, can we learn a convolutional neural network from a fully connected neural network? Theoretically, yes, but the search space is just too large. So I think that would be the trade-off between.
Do you have thoughts on how we bridge that? So in the sense that is there a way to use AutoML to basically say hey, hey human, please help me out a little bit. I'm seeing some sparsity over here. Maybe it's nothing. Maybe there's something here. And then you could go in and you could do this as a more iterative fashion. I think the thing that bothers me about the formulation, both for the structured sparsity and for AutoML, is this sort of notion that we a priori have already created the right basic architectures, because I just don't buy that assumption in the first place, right? I think all of our models are probably very wrong. So it's great that we can make them better, but then is there a way to sort of extend the framework so that you have sort of a more iterative process of improving these things? Or?
Yes, and so one suggestion is we can build an AutoML framework, but we human can propose some new architecture. We add it into the search space, and the AutoML will automatically define where should you put the new architecture. Mm-hmm. So in that sense, AutoML will help, but I think AutoML and the human experts will, if they work together, it will get much more benefits.
questions? Not, let's thank our speaker again.
Thank you.